Okay, today let's start the tutorial. Sorry, I'm a bit rushed just now. I just finished giving a substitute lecture. A bit terrible. Okay, today we are going to talk about what we call the bias variance decomposition. So I think Prof. Harold provided a very good intro to this bias variance decomposition. Anyone remembers what this decomposition tells us? What does it try to tell us? Anyone? This will be helpful for your assignment. What does the bias variance decomposition tell us about? So usually we would see that if we try to train a normal ML model, the error will be based on what data set that we have, right? The training data set. But then Prof. Harold mentioned that, oh, every time we sample, right, this will be a different data set. So what we want to obtain now is instead of having a normal error per data set, right, what we want to have is kind of a generalization error. This is the error that is obtained if you train across all possible data sets that we have, okay, all possible samples. So this generalization error, we have shown from the math that this can be decomposed into bias squared or bias plus variance plus what we call the noise. Okay, this is kind of the error also. So we have shown also inside the lecture that there's this bias, variance, and also noise. So the important one for this tutorial is that you should be able to understand what this notation is, because once you get a hang of what each of them actually mean, then this will be very easy already. Okay, so when we say the bias is actually taking this as your average y minus average t. Okay, what this tells us is average y is yx is essentially any predictor based on this data set. So when we take the average of this predictor, it's saying that if I regress so many times, right, what is the average line or average curve that I provide? Okay, minus this is basically the average target. So if my target is something like, or if my target is like this, right, then if my bias is somewhere like this, then this will be the difference that is captured by the bias. How far is it from the actual target between the average regressors? Okay, variance is between each predictor, compare it to the average predictor. Okay, so one curve that I generate, compare it to the average of all curves. How far is it from happening? Okay, so for example, if I generate like, say, this is the first curve, then this is like my second curve, something like this. Then if I have another third curve, then something my average will look a bit like this. Okay, then this will have a bit higher variance because the other curve has like a far difference from the average one. Okay, whereas the noise is essentially from your average targets, compare this against your true targets. This will tell you how far your target is actually wrong. Okay, so something like, for example, if your target was supposed to be a line, but then the data points that you have is like, oh, this is the t values that you have, then this is the noise. Okay, so note that this noise part is not caused by your model, but this is already the problems that exist inside the data set. Okay, so once you understand this generalization error, then this should be okay already. What we want to show today is on rather, how do we actually show whether something is unbiased or not? And we today want to see what would be the effect of we add another regularizer. How does this affect our bias and variance? That is the essence of today's tutorial. Okay, so let's move on to the tutorial question. In this tutorial, we are going to explore the bias variance decomposition, specifically on this equation. So I understand that this tutorial might be a bit more deep in the math side. So if you are confused at any point, just raise your hand. Feel free. Okay, I'll try to go through this step by step also. So in this bias variance decomposition, we notice that our goal is not just to minimize the training error depending on the data set, but what we want is to obtain a good generalization error that works on any samples that we have. Okay, so we want to obtain a low generalization loss. This is basically the expectation of your loss given your y, given your x, given your targets, and given your data set. Okay, so we want to find the expectation across all sample data sets that we have. Okay, that's essentially our expectation here. So we see that this generalization error will be split between variance, bias, and noise. Now we'll see through each of these small problems. First one is, we assume, this is an important assumption here, we assume that we want to implement a normal linear regression where our targets is equal to a linear function plus a certain noise. What does this part mean? This part means that, say for example, if my target was supposed to be a clean line, something like this, right? But there's a certain noise. So my data set that I will give out, right, the t values will look something like this, where there's a certain noise. The noise is distributed according to a Gaussian model. Okay, so this orange part is what our data set has. The green one is what the WTX was supposed to be. Okay, questions to this point? So now we assume that our target follows a linear line with a certain Gaussian distribution for the noise. That's our important assumption. First one is we want to explain why when we take the average of all the targets, we will get this X transpose W star. How do we get this part? So part one, we see that we define that T of X. Okay, T of X, this is a factor X. This is equal to W star T X plus the random noise. Okay, this is the initial one. So I can say that since this epsilon will follow a Gaussian distribution, right? Wrong notation, sorry. This should be, yeah. So this epsilon follows a normal distribution with the mean at 0, variance at 1. Okay? So what happens when I want to plot the distribution of this Tx? What will happen here? Note that this W star X, right? This is what the target was supposed to be originally. So this is kind of like a more constant value. Okay? It doesn't depend on any randomness, any distribution. So in the case that we add another error here, now this T will become a probability distribution. How do I model this probability distribution? I can actually model it this way. P of T given X. Okay? This will now follow what distribution? If I combine a Gaussian with a normal constant. Now this will still be simply a normal Gaussian still. Okay? It will still be a Gaussian. But the difference is that now this Gaussian will have a different mean. What is the mean? Remember that if we do expectation formulas, right? If I have, say, for example, expectation of AX plus BY, where these are two random variables, then this will be a linearity of expectation. Okay, something like this. But expectation itself, sometimes we take it as the mean also. Okay, so under the case of this part, if I take the expectation of this, okay, this is not randomly distributed, so the expectation is just itself, right? Plus the expectation of this epsilon, which is just the mean. So overall, if I combine this, you can imagine this Gaussian initially from 0, 1, this is shifted by WTX. This is shifted, okay? So it's added, all the values are added WTX. So the Gaussian now shifts, but the shape itself is still the same. It's just that the position is shifted. So here, this will now follow the Gaussian of T given. Now the mean will be 0 plus W star TX. Okay? Note that this is because when you add the WTX to every part of the Gaussian, right, this will just shift down. This will shift the mean, but now the variance will remain the same. Okay, this is the first part. Any questions? Thus, when this happens, if I want to get what is the average T here, right, then I will just get what is the expectation of this. Expectation of this part. Say given P of T of this N T 0 plus W transpose X. 1. Okay, this expectation is just exactly the mean, which is just the 0 plus W star transpose X. Okay, I think this one I should put a small x, because now I use T of small x. This one is a big X. Okay, so once I have this, then this is just W star transpose small x. Okay, but it's important to note here that at this point, this small x is just one single data instance. It's no longer a factor, right? So you can imagine it this way. This W star is going to be 1 times, say, M set of features. Then your X itself is just now M set of features times 1, because it's only one data set. Okay, so overall, this will now be a scalar value. Okay, since this is a scalar value, then this WX transpose times X, this is W star transpose times X, this is essentially the same thing as X. This is essentially the same thing as X transpose W. Because it's a scalar, right? So if I try to transpose this, now this will be M times 1. Transpose this is with 1 times m. So if I do x transpose times w star transpose transpose, this is just the same thing because it's a scalar value. So it's like a dot product of two factors. Okay? Questions to this point? Any questions? Seem puzzled. Okay. Okay. Now we go to the second one. Now that we already know that Tx small x is equal to x transpose w star. Okay, but actually we might not use this for now. This is just for us to demonstrate how we can obtain it for each single data set. Now for part 2 is where we want to see it how if we represent this as a factor. Okay, for us to easily visualize this, we can actually see that this xd we can construct it this way, such that this will be an array where this is x1 transpose, this is x2 transpose, so on and so forth. Okay, this is for us to visualize this easily. Now what we want to model is that we know TD is equal to XD W star plus, this is what we want to get, which is TD equals to XD W star plus epsilon factor. This epsilon factor is essentially it's kind of a random factor which contains all your epsilon values. This is essentially what we are doing. Okay, so we want to actually express it this way. First off, let's see what we have so far. We have your TD. TD is equal to, let's say Tx. So if I give you one single data set instance, right, this Tx is equal to, basically just now we've shown that this is just W star T, this x1 plus E. Okay, note that this is just the normal T, it's no longer the average T. So my epsilon is still there. This is just for one single x value. Okay, this is what we have in the initial one. Now, what if we want to put this against the all of the possible data set? Okay, one logical way of doing this, or how I can approach it, is you will have to see that your TD will now become some form of a factor, where each of these will be, say, this will be of Tx1, this will be Tx2, so on and so forth. Tx up to the size of your D. Okay, quite logical, right, at this point. So my TD is just a factor consisting of what is the target for x1, target for x2, target for x size D at the end. Okay, once I have this, then I can just decompose them. I can show that this part is just W star transpose x1 plus epsilon. This is W star transpose x2 plus epsilon, all the way up to W star transpose x, the last possible data set plus epsilon. Okay, to this point, I think this will be a bit clearer that I can actually separate out the epsilon values. Okay, this will be just the sum of two arrays. The first array is going to be this W star T x1, W star T x2, so on and so forth. Plus, this will be the epsilons. Which, at this point, we know that this part is just the epsilon factor. Okay, clear on this? Any questions? Now we move on to this part. How do we decompose this? So we see that this part, how can I modify this to actually incorporate both my W star as well as my XD, where my XD just now I defined it this way. XD is equal to, this is my x1 transpose, x2 transpose, so on and so forth. Okay. To obtain this form of factor, then I will have to get, say for example, if I get another W, this is my W item. So this will be, say, initially this is W1, W2, W, so on and so forth. This is my W factor. Okay. My end goal is I want to do, for each of these factor, I want to multiply them by x1, x2, so on and so forth. So how can I do this? So you see that the goal is that this row must be multiplied by this factor, right? Make sense? This row must be multiplied by this factor. So does W come first, W times X, or X times W? Matrix multiplication will tell me that whoever I want to multiply the row with, this will come first. Row multiplied by column. Row multiplied by column, right? Okay? Matrix multiplication. So at this point, if my end product I want to get, this is basically W multiplied by x1, rho times W multiplied by x2, rho times W, all the way up to xd. I can achieve this by actually multiplying my xd with the W. Note that my W itself is a column factor, right? Okay, so this already is a column. If I cross multiply this by my xd, then this will multiply every row of xd, which is basically every instance, with W. Okay, any questions to this point? So at this point, this part, we have shown that this part is just xd W star. And thus, we have shown here that in the end, my TD is equal to xd W star plus the epsilon factor. Where epsilon factor is just the factor containing all your epsilons. It's a column factor. Okay, questions? Okay, now we'll move on to part 3. Part 3 is where we want to use part 2 to show that when we want to take the average of all the predictors that we have regressed, this average predictor must be xdw star. Okay, so in this problem, we are actually going to explore more about expectation today. Okay, so we will leave probability aside for now. So how do we solve the part 3? Let me add another page here. Template just number 1. Okay, so here there's two property of expectation that will be useful. First one is, if you have, just now the linearity of expectation. If you have two random variables, they don't have to be independent. You can actually separate out the expectations. That's the first property. Second property that we can use here is that I can actually model, say, if I have the multiplication of two random variables. Say if I create a new random variable called xy, okay, I can actually separate this out to be e of x multiplied by e of y. Under which condition? When can I do this? When x and y is independent. Okay. So only when the x and y are independent, we can actually separate out the expectation by a multiplication. Okay, clear this? So once we have this, then we can just insert our answer for part 3. So for part 3, our goal is to show that the average of all predictors, this will be equal to xd w star. Okay, so for this, we will have to utilize the initial predictor formula that is given. So our predictor x given, our predictor of x given a certain data set is equal to, this is basically the formula we obtained from the ridge regression. You can check lecture 1 for this. So remember that this part is just our, this part is where we have the pseudo inverse, right? That we discussed in the first tutorial. So at this point, we now insert the value of TD that we have obtained just now. So from part 2, we have shown that TD itself is equal to your xd w star plus epsilon factor. This is what we obtained in part 2. So we are trying to substitute here. Then I will get my y x given d. This will be xt, this whole equation. Then we put in the TD. The TD is just, this part is just xd w star plus epsilon. Okay. Here I will do another part where if I see a bracket, then I do a multiplication, right? There's an addition inside this bracket. So here I will use basically the distributive property where I can separate this into two separate terms. Okay. When I distribute them, then I will get this part is just xt, capital X dt, xd negative 1. I think I should put this as small x first for easier. Then this one is just capital xd, t xd w star plus basically this whole thing. Okay. So when we take this expectation, now you already see where the pattern will be coming, right? Because when we split them into two separate summations, now my expectation, we can use the linearity of expectations. Okay. Let's call this will be the first term. This part is the second term because my space is a bit small to write everything here. Okay, so when I do the expectation of y, let's take this over PD. Okay, because we want to take the expectation of these regressors when I regress them along different data sets. Okay, I want to regress them with different samples, then I want to find what is the average of all the samples. Okay, that's why my expectation is with respect to the data set D. Okay, so this is, I think I need to put this one. This is my yx, which is equal to, for all the y's that I have, what is the average y over all the samples that I have. Okay, so this part will give you basically the expectation of, for simplicity, I'll skip the PD here. Basically, this is the expectation of the first term. Yeah, expectation of the first term plus this will be the expectation of the second term. Okay, clear on this? By linearity of expectation, if I have the summation, I can split them. Okay, now let's try to compute what is the expectation of, let's try the second term first. Okay, we want to find what is the expectation of the second term. How do we do this? This will just be the expectation of my small xt, capital XD transpose, capital XD inverse, XDT, XD, hey, this should be epsilon. There's an epsilon here. This would be, yeah, this will be XDT epsilon. Yeah, so this is the second term. How do I compute this? How do I compute this expectation? My question is, what does this epsilon follow? This epsilon follows which distribution, if we still recall from problem 1? It follows normal, right? Normal of these epsilons given 0, I means that each of the epsilon will have variance of 1. Okay, so it's just the identity matrix there. The covariance matrix is just the variance of 1s itself. Okay, so this epsilon follows this Gaussian distribution. Thus, the next question is, can I say that this epsilon is independent of this? This epsilon doesn't depend on any part of your x, right? It's a noise that depends on how is it distributed, modeled by the Gaussian distribution. Okay, so this epsilon is independent from the first term. When this independence happens, then I can put this common trick where I can separate out this into the first part times the expectation of this E. Okay, I will just skip this part first. I don't want to write too long. Okay, questions? So we can separate out the epsilon, becomes expectation of that epsilon times the original expectation, the first half. Now next part is, what is this? What is the expectation of epsilon over all the possible datasets? Why is it 0? Exactly. This is the expectation of a Gaussian. Okay, remember that the expectation of a Gaussian is just the mean of the Gaussian. We take whoever is the middle point, the most dense point. Okay, so this part actually falls down to 0, following the mean of the Gaussian, which is basically 0. Okay, since our epsilon itself follows a Gaussian distribution of 0, 1, thus we can say that the mean is 0, expectation of this epsilon is 0. Anything multiplied by 0, this will fall down to 0. Okay, so this is the common trick. When you see this epsilon coming up, if it's independent of the start one, you can actually split the expectations apart. This will be 0, so anything multiplied by 0 is 0. Okay, questions? Now when this happens, we can now proceed to the first term. The first term will be basically just inserting our screw it. Okay, Now in the first term, what we need to do now is to just show that the average regressor will actually fall down from the first term. Okay. So let me just zoom in. So we have shown that just now, this average regressor is the expectation of the first term plus the expectation of the second term. But then the second term we have shown that is 0. So we just go with the first term only. So this will be the expectation of whatever is inside my first term. Expectation of the first term is essentially I'm taking the expectation of this part, which is small xt, capital XD, T, XD inverse. Then I do another XDT, then an XD with a W star. Oh, screw it, this star is in bottom. Okay. Remember that this part is just from our problem 1. Okay, where we do the T is equal to XDW star plus epsilon. The epsilon part is removed already. So now this is just the remaining one. How do we simplify this? Tutorial 1. You see this bunch? You see this bunch? This is exactly the pseudo-inverse application. Okay? So the moment that you see this XDT, XD inverse multiplied by XDT, XD, this will ultimately result to identity. Okay? So this part is just the expectation of small xt. This is identity matrix times the W star. Or rather, this is now the expectation of small xt W star with respect to all the data sets. Okay? But note that at this point, it now no longer depends on my data set. Okay? Because there's no more D items inserted. Just now my XDT here, right? These are all depending on my D. But now when I do the Moore-Penrose pseudo-inverse, this part collapses into an identity matrix. Now it's just small x transpose I W star, which is now just small x transpose W star. It no longer depends on my D. Okay? So what happens now is, this essentially just happens to be XD W star, which tells us that this average predictor for Y is essentially the same thing as I'm taking all of the pure X, not just the sample X's, but all of the pure X multiplied by my weight. At this point, any questions? Okay, once this is done, then we want to show the last part, explain why the bias is 0. This one I think I don't need to write. Bias is given by average predictor over all data sets minus the average target. We have shown here that the average target is just small x transpose W star. Then we have shown that here the average predictor is small x transpose W star. Both of them are the same terms. So when you take the bias, Y bar minus T bar is 0. That's why 0 squared is 0. Conclusion is when this assumption holds. When you do linear regression will act as what we call an unbiased estimator. Now comes the next part. What is an unbiased estimator? What do you mean that something has no bias? Okay. So let me just share with you something. It's the same notebook as what we have seen in the lecture, but I modify a bit. So let me just run everything. So now I converted the lecture notebook into just simply this small line, okay? So in the lecture, we discussed that it will be it's like a sine wave. But for this one, I just converted into a linear line, okay? Here you will see that this is my line. This part is my data set, my data points, okay? The ones that are sampled. As you can see, there are noise. Wait, okay, it's gone. Yeah, a bit slow. Okay, anyways, what I'm doing now is I'm actually using this is my data set, which is the blue dots. Then the red one is essentially what is being created by my model for that data set. Okay, so I repeat this for many times. Then I will see that it will produce me all these red lines. Then all the red lines will form like this. Correct? This is what we see in the lecture. When we take the average, you will see that the average is actually equal to the actual here. If I do a law of large numbers, the more I try, then this will be closer and closer to the actual one. Okay? The moment this happens, right? The moment this happens, you will see that this clips together. So my blue line, my y bar x. My green line is the t bar x. Both of them coincide. That's why y bar minus t bar is 0. This is an unbiased estimator. Okay, questions to this point? Of course, you have small variance again. This is the variance. Questions? So what this means that under the case of this assumption, our assumption is that the data points follow a linear distribution. So when you have a linear distribution, then you use a linear regression. This will work. It will predict the actual value. That is what we mean by the unbiased estimator. Okay, clear on this? If we clear on this, then we move on to the second part. So don't be scared about the second part. In fact, you don't need to understand the diagonalization to answer this. Okay. So for the second one, we want to actually just show some form of the diagonalization. So for those who have forgotten your MA 201, this is essentially what we call diagonalizing. Okay, which tells me that if I have, say, a certain matrix, I can actually create a diagonal matrix of it by first creating a matrix that contains the eigenvectors. Okay, then this A can be decomposed as this eigenvector matrix multiplied by a certain diagonal matrix multiplied by the inverse of that eigenvector matrix. Okay, if I want to get the S, then usually I will just write the S as we inverse the Q, A, Q. Okay, this is the common property that you have seen in your MA 201, chapter 6. You can look through again. But we are not going to go into the diagonalization part today. What we want to show now is that if A can be decomposed this way, can I show that A plus lambda I will be decomposed this way? That's my goal for today. Okay, so let's try to do this problem. This one is actually quite short. Let's take A is equal to QS Q inverse. Assuming that Q itself can be invertible. Okay, that's my common assumption here. So when this happens, I can do A plus lambda I is essentially just doing this QS Q inverse plus lambda I. Okay, so this lambda I can do this way also. I can actually put it in terms of saying this will be lambda QQ inverse. Still the same thing, right? Okay, then this part I can actually further drill down. This can be written as lambda QIQ inverse because anything multiplied by identity is itself. Then the moment this happens, this lambda can be multiplied together with the I. Note that lambda is a scalar. Okay, it's a constant here. So I can actually bring it down, multiply to the I, then this will still work. Okay, so this is just manipulating it by identity matrices. Then I just put the lambda back inside the identity matrix. Okay, questions at this point? So at this point, my equation will now become this is just QS Q inverse plus Q lambda I Q inverse. Note that the Q itself doesn't have to relate to this I, but then I know that Q inverse is just I. Okay, so I can rewrite it this way, then I insert again the I here. This is one way of expanding it. Any questions? So when this happens, now I can group them together. I can apply the distributive law again. I notice that both of them have Q in the front. Okay, so I can combine the Q's together. Now this will be Q multiplied by, this will be SQ inverse plus lambda I Q inverse. Pre-multiplication, because the Q comes in front, so the Q has to come first. Okay, then I will see that inside this, right, both of them have Q inverse at the end. So I can use the distributive property again, but then because the Q inverse happens at the end, I have to maintain the order of the multiplication. So then I can separate this further down. This will be Q of, this will be S plus lambda I Q inverse. Questions? Note that I cannot say Q inverse at the front because I have to preserve the order. When this happens, then I can insert this will be association of matrix multiplication. I can actually just put the bracket out. This will be S plus lambda I Q inverse. And I'm done. Okay, so this S plus lambda I, this one is essentially just similar to having a diagonal matrix of S1, S2, all the way up to Sn, say for example. Then this will be plus lambda plus lambda. Then all the remaining part is just zeros. Questions? Any questions? Okay. If no questions, we move on to the last part. Last part here is where we go back to ridge regression. Now, what we want to show here is what happens when we have a regularization term. So, in ridge regression, you can check again your lecture 1. The only difference is that inside your ridge regression formula, now there's this lambda I. Okay, just now at the start we don't have this lambda I, but now we have this additional lambda I. So the question is, how can we manipulate this? I would need to clarify with you first. Based on the solution as provided, you are not actually expected to come up with what is the value at the end, but you just want to see how is the bias being shown. Okay, so you will see that in my solution later on, you can see some form of substitution. Okay, so that it will just be a form that is easy to look, or else this will be a bit tedious. So how do I do this part? First one is, we try to do something similar. If our concern is that we want to find what is the bias term, okay, if I want to find what is the bias term, then what are the two terms that I need to determine the bias? By now I should make it second nature. Bias is equal to expectation of y bar minus t bar. So I need to find what is the average regressor, what is the average of all target values, given that my target has noise. Okay, t bar is, we have shown already. T bar, the t is still the same, so I can still put t bar as this, just the xtw. Okay, this one I will not touch. Still the same part as the previous questions. The one that will be changed is what is my y bar, because now my y changes. My y now has an additional regularization constant. Okay, so I try to find what is the y bar. If I want to find the y bar, then I will put the definition. This will be basically just the expectation of, across all the data sets, small xt times this whole thing. There's a plus lambda I inverse xdt, xdt, then we insert what is the t here. Okay, so insert the t again. This will be xdw star plus the epsilon factor. I think I should put a square bracket instead. Okay, so from part 2, so from problem 2, we have shown that I can actually just decompose them. I separate out the epsilon factor, then the second term will go to 0. Okay, so that one I will not rewrite again. Basically, I can just cut off the lambdas here. Then now this will just be small xt, capital xdt, xd plus lambda I, inverse xdt, xdw. Okay, clear on to this point? Any questions? Now this is where some of the magic will happen. Okay, so what is the magic that I'm going to do here? We are going to make some new variables, new matrices that we will create. Okay, so here, let us set. Just now we have shown that if for, I'll use another color. So just now we have shown in problem 2 that any matrix A that has a full rank, I can just separate this out into Q, S, Q inverse, right? Okay, so what if set A to be equal to xdt, xd. Okay, so now every time I see xdt, xd, I will call this A. Okay, which we assume that this can be written as QS, Q inverse. Why can we do this? Because your xdt, xd is invertible. Okay, then I will know that they will have full eigenvectors. Okay, so I can do this. Xdt, xd is equal to QS, Q inverse. So this part is now A. This part is now your QS, Q inverse. When I do this lambda I addition, okay, now this will form me, from the previous problem, this will be xt q of s plus lambda I q inverse. So now this one I will just change this part into, this will be my qs q inverse. Okay, so whenever I see the xdt, xd, I replace this by A, which A itself I can decompose them into qs q inverse. Questions? This part is a necessary step here. Okay, So when this happens, next part I want to do is we make another assumption again. Okay, we set this S prime to be equal to my S plus lambda I. Okay, solely because it will be easier to see later on. So when this happens, now this will become expectation of small xt. This will be q s prime q minus 1 q s q minus 1 w star. Okay, note that when matrix multiplication, if they are in the same order, they are associative. So I can actually multiply these two things together first. I notice that q inverse times q, this will just be the identity matrix. Then now this will be eliminated. So now this will be small xt q s prime s q inverse w star. Okay, so here, okay, the solution will actually assume another one, but I'll just keep it this way because I think this is quite clean already. Okay, so from this point, what I need to do now is to now determine what is the bias. How do I determine the bias? The bias is just the expectation of average predictor minus average target. Okay, so this is the bias. So now just put this in. This will be the expectation of expectation across all the data sets of this xt q s prime s q inverse w star minus this t bar x we have shown just now. This part is just small t, small xt w star. Okay, this part is just plugging in the values that we have found from the top plus the values that we have seen from t bar x. Okay, when this happens, this part is where there's another magic that will happen here. The next magic part here is that I want to convert this into some form of expectation such that I can combine it with the previous term. Okay, so what do we do here? When we do this way, I can actually just do this expectation over x. This will be expectation over PD of this whole part minus. Now since this is a constant, right? So if I take any expectation of this, this should not be any problem. Okay, we put this xt. Then to follow this form, I will just put this as q inverse w star. Note that when I do q inverse, it's just q times q inverse, which is just identity, which is just doing nothing. Okay, so this part is just an additional way of expanding it further. Why do I do this? So that I can merge these two things together. Okay, questions? Now when I have this part, I can just take this expectation over, this will be expectation over all of the PD. Note that actually this doesn't depend on PD anymore. Okay, when this happens, I can just combine them. Now this will be expectation of x, expectation of PD, or this one there's a square. So this will be xt q. I can now combine this s prime s together with the I, q inverse w star. Okay, yeah. So at this point, it's important to note here that because of the linearity of expectations, I can combine these two things together. So this will be expectation of the first term minus the second term combined. Then I see that from the first term, second term, both of them share the same part at the start, both of them share the same part at the end. So using the distributive, I can combine the s prime s minus I together. Okay, so this is essentially what my bias is going to be. Questions? So, what does this mean? What does this mean? First one, note that this part is non-zero. It can be non-zero here. Okay? We don't know what this value is because we don't want to expand this further. It will be too nasty. But what we want to show is by having this lambda I, when we introduce this regularization term, our bias is no longer zero. Just now we have shown that when we put y bar minus t bar, it's the xtw minus xtw at zero. Okay? But here when we introduce this lambda I, now this regularization constant puts you with a bias value. Okay? Plus, the second thing you will need to see here is because of this square term. this square term will tell you that your bias is always non-negative. Okay, it's either 0 or positive value. That's why the bias will be there. So that's the essence of today's tutorial. You will see that when you introduce a regularization, your bias will be present. Now, how do you imagine this? I will show you in the same notebook. Yeah, screw you, collab. Okay. So I will introduce here, this is just basically I'm trying to pick a lambda from these values. You will see initially I set my lambda as 0. Lambda 0 means that there's no regularization done in the first place. Let me zoom in. Yeah. Lambda 0 means no regularization. Then I start my lambda small. Then I go all the way to the end. Okay. It's important to note that when your lambda goes to infinity, actually this will become a straight line. Standard at 0. Okay. Which I will show later on. So let me try to run this. And let me show you all the values here that we have found. I think for now I'll just zoom out. When lambda is 0, this is exactly the same case as we have seen just now. The moment that the lambda is 0, no regularization, thus this is an unbiased estimate. Because you want to predict, because your data itself follows a linear distribution, a linear form, then your model is also linear regression. So you can predict perfectly. Okay, if you regress it again, lambda 0. Lambda is equal to 2.0 times 10 raised to negative 9. Still looks very small. So you will see not so much an effect. Actually, not so much an effect until you see that it will go to higher values when lambda is equal to 3.7. You see how it deviates. Okay, at this point, the bias is just for each point here. How does it differ from the actual line? Okay, that's where the bias comes in. Remember, Prof. Harold draws at this distance. For all of the x points, how is the average one differ from the actual one? Now you see that there's some deviation. Okay, I'll scroll down further until we reach higher values of lambda. When lambda is equal to 1, you see that this starts to deviate much more. When I set this as 10, what you see now is that now this will follow a gradient 0. Okay, now this will follow a gradient 0. Up to when I reach a very high lambda equals to 100, now you see this will be centered at 0. That means at this point, your regularization term, right, is so overpowered that none of your weights even matter. It's just centered at 0. Now you see that the bias is very high. Okay? Is the variance high? Might be. You need to consider a generalization error at this point. Okay? But what I'm showing here is the moment that your lambda actually increases, you actually have this bias will form higher. Okay? That's the essence of today's tutorial, where you've seen that at the first point, you assume your regression, you assume that the model follows a linear line, then you use a normal regression with no regularization, is unbiased. The moment you introduce regularization, higher the lambda, this will be forced over to a straight line. That's the essence. Okay? Questions? If no questions, then that is it for this tutorial. Make sure to scan your attendance for those who haven't. Else, you're free to go. Thanks.